So good morning, everyone. So welcome back. So today, Professor Sreekrishna, so he will be giving his last lecture, this workshop. Okay. So over to you, Professor Sreekrishna.
Thank you, Professor Abhijit Pal. Good morning, everyone. So in today's lecture, we will see the proof of the Svarc-Milnor lemma, which is said to be the fundamental lemma of geometric group theory. So hence the title there. And so we will basically try to set one small meta goal of the geometric group theory using some definitions. We will try to see groups as geometric objects. We did so using calligraphs in 2 lectures ago, and now we sort of want to put a metric, nice enough metric on these calligraphs, and then study these groups as geometric objects. Okay, so one of the fundamental impediment in this is that you recall that we had the calligraph of Z with a generator 1 versus the calligraph of Z with generating set 2, 3. Okay, so recall this example where the first calligraph is like that. It's basically looks like the real line, with vertices at these integers, whereas the other one, it looked somewhat like that, some picture like that. Okay, so this was a calligraph. So now immediately we cannot announce the path metric to be the metric and get isometries between these 2 calligraphs. So for example, 0 is connected to 2, and then like that, and then 0 is not directly connected to 1. So the distance, if we were to announce this distance as distance, then the distance between 0 and 1 in this calligraph is 1, whereas the distance between 0 and 1 here is not 1, it is 2. Okay, so you can check that you can get there with a path of length 2. So certainly these will not be isometric if we just announce the path metric. Okay, so we need to do more. This can get more complicated if we take more complicated generating sets, and the group, this one is a very simple kind of group, and then if we take more complicated groups, this can really get complicated. So you remember that I assigned an exercise in the calligraph section. I asked you to, I actually asked an open question that does there exist a calligraph of Z plus Z where you can get 0, 0 to PQ. For which PQ can you actually connect it with an edge? That sort of question. So go back to that lecture. So any a semi answer to that is you can connect up any 0, 0 to PQ, put it in the generating set anyway, no harm, and so you can make that distance 1. So that will alter distances heavily. So it seems, after a good thought, it seems that there is no direct way out of it. We cannot preserve the nice local structure of these metric spaces, which are obtained by announcing these calligraphs as path metric spaces, and trying to get isometry between them. Okay, so hence we need grosser definitions which forget the nice topological information, if you will, on these sort of spaces, metric spaces. So what that means is that we have to actually forgo continuity in order to make the calligraphs of Z with whatever finite generating set sort of equivalent. Okay, so we will see that. How do we do that? We'll see that. Firstly, I will assume that you know a metric space. I'll not define a metric space, and then the definition of isometry. When is a function from x to y in isometry? Easy, right? And then what is an isometric embedding of a space into another? So those are easy definitions, and you can anyway recover them from the following definitions that I'm going to make. So here is bi-Lipschitz equivalent. Equivalence. So firstly, let x dx and y dy be two metric spaces. Okay. And a map f from x to y is called bi-Lipschitz embedding. I'll write BM for short. If there is a constant, a real constant C positive, such that if rather not if, for every x prime in x, 1 by c times the distance between x and x prime is less than or equal to the distance in y of f of x and f of x prime is less than or equal to so we see these sort of relations when you take so various metrics on R2. One shows that the square sort of balls in R2 with respect to a certain metric are equal to the round balls by Euclidean metric, etc. So there are those exercises, for example, in a beginning course in real analysis. So bi-Lipschitz equivalence is basically motivated by that. Firstly, there is this bi-Lipschitz embedding from x to y. So clearly this map will be injective. Okay, the way it is defined, you can easily show that this is injection because of this relation, these inequalities. Okay, and we now define equivalence. F is, so I'll put a bullet, F is bi-Lipschitz equivalence rather, if it is a bi-Lipschitz embedding, a BM, okay, and if there is an inverse, so to speak, if there is a bi-Lipschitz embedding BM G from y to x, so you can go back via a bi-Lipschitz embedding in the opposite direction, such that F composed with G is identity on y, and G composed with F is identity on x. Okay, so x and y in this case are said to be bi-Lipschitz equivalent. Okay, if there is such a bi-Lipschitz equivalence between them. Okay, so that's bi-Lipschitz equivalence, and this sort of still preserves the local structure around the graph of z. So I'm having the graph of Cayley graph of z in mind when I talk about this. So the following properties of this bi-Lipschitz equivalence can be easily verified. Okay, like I mentioned, a bi-Lipschitz, so a B embedding is injected. Okay, very easy. Okay, and then a bi-Lipschitz equivalence. Now I'm talking about equivalence, not the embedding. This is a homeomorphism. Clearly, it's a homeomorphism because the with respect to the underlying or the topologies induced with respect to the metrics, you can show that balls are broadly preserved. One ball embeds into the other ball embeds into one. So, and it's an open mapping sort. So it's an open mapping, and so this is a homeomorphism. Okay, this can be easily checked, all of these properties. So, and then a bi-Lipschitz embedding is an equivalence, is a bi-Lipschitz equivalence if and only if B is, so it is a bijection. So the converse part of this is interesting. One direction is easy. If it is an equivalence, then automatically, or it's easily a bijection, at least by Schroeder-Bernstein. If there is an injection in this direction, there is an injection in the other direction. So it will be a bijection. But if it is a bijection, it will be interesting to show that a bi-Lipschitz embedding is automatically an equivalence. So try to construct an equivalence or the inverse map using the bi-Lipschitz. So these properties are easily verified. Okay. Fine. So that's a bi-Lipschitz embedding. Like I already mentioned, this is a homeomorphism, so it still preserves that continuity, which is not to our liking. Okay. So now, having loaded ourselves with this definition, we will once again visit yet another familiar friend of ours, a Cayley graph. We have seen this Cayley graph. Let us look at the Cayley graph of Z plus Z with respect to the generating set 1, 0, 0. Okay. We saw this, that the Cayley graph will be a grid, the lattice in R2. So let me mark this as the x-axis, y-axis. Okay, in R2. So you get this, this as the Cayley graph. Okay. So now the goal is basically to sort of, well, if we put some sort of a metric here, announcing path metric. So basically any two vertices are at a distance 1 if they are connected by an edge, that sort of path metric. We want to be able to see that this looks like R2. Okay, so why do we want to do that? Well, Z plus Z has a nice action on R2, and then there is this. Well, I'll not put those hashes. So this a nice action on R2, and then you have a quotient space which is torus. You may or may not have looked at that. Well, you're studying mapping class group, so you know that R2 quotiented by Z plus Z is a torus. With this generating set, you see that you have this grid, which more or less has the nice properties of R2, but it still does not have that sort of structure of R2. So geometrically, somehow you want to make these two equivalent, so that you can study this Cayley graph in a more in a meaningful way, in a nice way. So that's sort of one of the motivations. We'll see. We'll give one more example, sort of motivation for the fundamental theorem of GGT. Okay, namely the Svarc-Milnor Lemma. So we are going to somehow equate R2 and this one. So in order to do that, notice that this space, this graph space, has holes in it. And okay, so this graph space has holes in it, and so to say, it lost dimensionality with respect to R2. Okay, and so this is not going to be homeomorphic to R2 in any way. And bi-Lipschitz equivalence still is a homeomorphism. So bi-Lipschitz equivalence still is remembering some structure which is sort of not desirable if we want to achieve what I just said. So in order to do that, we make a definition of quasi isometry. So it's like an isometry that we want but never exists, because isometries are continuous maps, they preserve topology, etc. That's too much information. So hence quasi isometry. So firstly, let f from x to y, x and y are metric spaces, be a map between metric spaces. Okay. And you say that F is a quasi isometric embedding. That's the name. Like isometric embedding, it's a quasi isometric embedding if there are constants C greater than 0 and B greater than 0, such that F is a CB, we call it a CB quasi isometric. So it's a quasi isometric embedding if it is a CB quasi isometric embedding. What is that? That is, what is a CB quasi isometric embedding? That is for all x and x prime in X. It's like the bi-Lipschitz, but with a additive, with a addition and a subtraction to these factors. Okay, so minus b. So you allow the scaling of that metric dx. Okay, and then a translation is less than or equal to the distance in y of f of x and f of x prime. Okay, is less than or equal to c times dx of x prime, and once again you can add. So there is these constants minus b and b. The additions to those distances allow you now to be within a certain b of that particular space. So when you have a quasi-isometric embedding, so go back to this example, there is inclusion of the graph of graph of z plus z in R2. Well, we are painting it in R2. So you take points of this thing, and then points of the graph, and then they are within a certain distance of points in R2. Okay, so we'll see that this is the particular, this factor or this addition and subtraction of b is the one which allows for gives some room for there to be holes in the space. Okay, so now topology is totally lost. Okay, so in particular these maps will not be continuous. We'll get to that. And a map f from x to y, or I'll say f prime from x to y, another map like that, has finite distance, or has a finite distance from the map f from x to y. Yeah, there's a question.
Yes, Rana wants to ask.
Just a minute, my chat is off.
Not chat, he wants to ask.
Yeah, okay, there is a Rana, yes, please.
Hello, sir. Good morning. Sir, if we take C is equal to half, okay, and B is equal to G.
E is equal to half and B is equal to 0. Sorry, C is equal to half and B is equal to 0.
Yes,
His audio is sort of.
C is greater than or equal to 1.
Yeah. Clearly, if you cannot take C is equal to half and B, anything like that. Oh, I'm in trouble. So you cannot take that way because the inequality here will not hold.
Yes. Yes.
Right. Is that the question?
Yes. Yes.
Yeah. Please reduce these sort of things. Right. It's easy. Yeah. Okay. Yeah. So you cannot take like that. Sorry. Okay. So a map f prime from x to y is at a finite distance from f, which is also from x to y, as in the previous definition. Okay. So if there is, so it's between metric spaces. That's all I want to say. If there is a constant C, positive constant C, such that for all x in X, the distance in Y of f of X and f prime of X, okay, these two stay within C of each other. Okay, this should happen for all x in X. Then you say that f prime is at a finite distance from F, okay? Or you can say at a distance C from F, if that is needed. Okay, and then the map F now is a quasi isometry. So we define quasi isometric embedding if that inequality holds. Okay, and I sort of explained the intuition using the Cayley graph there. So the map F is quasi isometric embedding, sorry, isometry, quasi isometry if it is a quasi isometric embedding for which there is, you would expect there is an inverse of sorts. Okay, there is a not exactly an inverse, there is a quasi inverse, because these functions need not be bijective. Okay, so you cannot exactly expect an inverse. Quasi inverse quasi isometric quasi inverse quasi isometric embedding. Okay. So what is this? What is this quasi inverse? It is a map G from Y to X such that G composed with F has finite distance from identity of X, and F composed with G has finite distance from identity of Y. So you can't expect the composition to be identity, but what you can expect is that it is at a finite distance from identity. So once again, our motivating example here, if you take this R2, okay, so and then somehow squish it like that, each square you send it to its boundary, okay, then that map will basically satisfy this property. So you have sent all the points in that square to that boundary, and then you take the inclusion back from that grid to R2. So that will not be identity on R2. You cannot get back identity, but it will be it will be this quasi inverse, in the sense that it will be at a finite distance from identity. So the diameter of the square will basically be that finite distance. Okay, so let us take actually an example. Before that, I'll also say that X is quasi isometric to Y if there is a quasi isometry F from X. So it's a quasi isometric embedding with a quasi inverse. Okay, so when you have that, X and Y are said to be quasi isometric. So well, here is an example, a quick example, another example here. You take the space R, okay, metric space R, and then there are integral points. Let us say minus, I'll start from -4, -3, -2, -1, 0, 1, 2, 3. Okay, and then you can take the space of integers. Okay. The space of integers. So you have -5, -4, -3. So I'll write -4, -3. Okay, and then you can basically, so this is the this is the vertex set of the Cayley graph of Z, but we are still not talking about groups yet. We are just talking about metric spaces. So what you can do is consider this sort of triangle to be the crushing map. So this whole interval is crushed here. So this is -5, -4. So what you're doing is the integer which is the greatest integer which is smaller than the given real number. That is the map, right? So you can take this sort of crushing map. So I can, for one, I will draw a hash to indicate that that whole thing is crushed. Okay, and then what you can also do is take the space 2z, 2z, which is basically twice the integer. So it will only have -4, -2, and then 0, 2, etc. So here, consider the natural map. -4 goes to -4, -3 also send it to -4. Well, the choice is not unique, but let us do that, and then further. Okay, so map -4 and -3 to -4, etc. Okay, so these are maps which clearly will not be, I mean, at least this one is, okay, with respect to the topology on R, this is not a continuous map, right? So that is the topology anyway. On both of these, I'm putting the metric induced by metric on R. Okay, so there is a corresponding discrete topology on Z and 2Z. So one of the maps, the squishing map from R to Z, will not be continuous. But what is, what are some notes? The inclusions. First is that in this example, inclusions 2Z into Z. So you go this way, okay, and then this way, Z includes into there. So Z included into R. These maps are discontinuous. This one is discontinuous, certainly. The other one is not, but are quasi isometric. Okay, so yeah, when you have a quasi isometric embedding, it's probably a beginning exercise to worry about those constants C and B, but eventually, there will be a constant C, and B is all that is important. Those exact specific constants are not important. So for example, you see that any point on the real line is at most a distance 1 from this one. Okay, so you can take the constant without any scaling factor C, with C is equal to 1, you can actually take this constant B to be 1 as well. Okay, and then you can see that with CB, with that 1 and 1, you can see that this is a quasi isometric embedding, this one. Okay, the other one, it's clear that it is quasi isometric. So once again, it is 1, 1. Okay, and then, but these inclusions are not bi-Lipschitz equivalents, because bi-Lipschitz equivalence requires that you have a bijective function or a homeomorphism. Okay? But these inclusions are not bi-Lipschitz equivalent, as they are not bijective. Okay, and two, R to Z, you can give a map R to Z, send a X to, like I said, the integer which is less than it, and the greatest integer which is less than it. Okay, so the floor function, and from Z to 2Z, So now you're coming this way and this way. So these maps Z to 2Z, it's simple, just send n to, like I pictured there, you send n to n or n minus 1, depending upon whether n is an even integer or n is an odd integer. Okay. So these are, once again, quasi isometric embeddings that are actually quasi inverses to the inclusion maps. So that says that that says that these inclusions, okay, so you can actually check that. That's quite easy. Like I already mentioned, those constants, you can conclude that these inclusions are now quasi isometrics, right? So quasi isometries, and so we also want to say that Z and 2Z are bi-Lipschitz equivalent. They have the discrete metric space, and then the discrete metric, and then you have a you can construct that bi-Lipschitz equivalence. 2 is the constant. That scaling is 2. So, and then you also can say that Z and 2Z, well, this is easy, are not isometric, because 0 and 2, 0 and 1 are at a distance 0 and 2Z, whereas okay, and they are at a distance 2. So rather 2 and -4 and -2 are at a distance 1 here, whereas -4 and -2 are at a distance 2 in Z. So this is not isometry, this map, and R is neither isometric nor bi-Lipschitz. Equivalent to Z. Not equivalent to Z, and likewise this statement holds also for 2Z. Although R is quasi-isometric to both of the spaces. So with this discreteness, we sort of broke off from topology, but at the same time, certain key features remain with this quasi-isometric isometry. Okay, we will see in some time. Okay, so some properties of this, with that example, some properties of this quasi-isometric embeddings is the following. So in general, quasi-isometries is a quasi-isometry is one, not injective or surjective. You can see the above example. Okay, and it is not continuous. Same above example. Okay, 3. It's they do not have finite distance from any isometry. So yeah, so using this finite distance concept, this third property is telling you that you cannot redeem the situation somehow using that finite distance this thing. So quasi isometries are not finite distance from any isometry. Okay, so that would have put some sort of more uniformity on this thing, but that's not true. Okay, and then so I mean, so for example, in the smooth maps between manifolds, you can always find a smooth map close enough to a continuous map. That sort of theorems exist. So that is no longer true here. Okay, that sort of theorem is not true here. That property is not true. Okay, in general. And so these do not preserve dimension locally. Like in the Z plus Z example, that metric space Z plus Z. Okay, so they do not preserve dimension locally. Okay, so these are some of the properties. And we have an alternative characterization of these quasi isometries. So here is an alternative characterization.
What dimension are you talking about?
So if you have a dimension to a space like a manifold or something like that, that dimension is not preserved. Okay. So I'm only talking about that sort of dimension.
You are saying manifold, if two manifolds are quasi-isometry.
I mean, if you, you could have two manifolds are quasi-isometric, but the dimension is not preserved. Yes.
Can you give some
I think
example?
R and Z.
Rn and Z, yes, for example.
Rn and Z, they are not quasi-isometric.
I mean R and Z, not Rn and Z. R and Z.
And what manifold do you put on Z?
That is a zero dimension manifold.
Okay.
You just take.
I see. Okay.
In that sense. Okay.
Yeah, for example, if I take a strip,
Yes.
this
It is quasi-isometric to a line.
yeah, R cross a unit interval opening
Yeah, I got your point.
quasi isometric to R.
Yes, yes.
It is quasi-isometric to R.
The dimension is different.
I got the point.
Yeah. So so the point of these properties is to say that they can be quite crazy, these quasi-isometrics. However, there is a certain control over this craziness in some sense, in the sense of the lemma that we are going to see. But firstly, we will have the following proposition. Okay, so here is alternative characterization of quasi isometries. So a map F from X to Y. Okay, X and Y are metric spaces between metric spaces X dx and Y dy. Okay, is a quasi isometry if and only if there is a quasi isometric embedding. This characterization is useful for us later. So there's a quasi isometric embedding with, or I should say, F is a quasi isometric. Between this thing is a quasi isometry if and only if there's a quasi isometric embedding with quasi dense image. Okay, what is this? A map. What is a quasi dense image? A quasi isometric embedding with a quasi dense image. What is it? It is a map. Map F from X to Y is said to have a quasi dense image if there is a C, positive constant C, such that for all y in Y, there is an X. So I should say really for each y in Y, there is an X in X, such that the distance between f of X and Y is less than or equal to C. Okay. So So if that happens for a map, then you say that it has a quasi-dense image. A quasi-isometric embedding with this property you'll say that it has a quasi-dense image. And when a quasi-isometric embedding has a quasi-dense image, it will automatically be a quasi-isometric. One direction is easy. If it is a quasi-isometry, then this property is satisfied. The other direction is once again not difficult at all. What you have to do is because the quasi-dense image tells that for each y in y, there is an x which satisfies this. By axiom of choice, from among those points, you pick a particular point, by axiom of choice, and then you can construct a map G from y to x by taking any y and then sending it to that particular x which satisfies this property in y. So if we call that point as xy, then which satisfies among all the points which satisfy this property in x, there is at least one. So you pick one by axiom of choice, and then you can show that this is a quasi-inverse to this particular quasi-isometric embedding. And so that is the proof. So I just said sketch of proof. So it's easy, little bit of playing with the inequalities. Okay, so it's only this choice that will lead you to the proof. So this characterization of quasi-isometries is useful for us. And next, I want to talk about some properties of these quasi-isometric embeddings. So here is a proposition. So several parts to this. So every map at a finite distance from a quasi-isometric embedding, you would expect that is a quasi-isometric embedding. Okay. That's intuitive enough, right? So every map at a finite distance from quasi-isometry is a quasi-isometry. At a finite distance from a quasi-isometry is a quasi-isometry. So, unlike the earlier thing that I wrote, it's not at a finite distance from isometry, but within finite distances, you'll find other quasi-isometrics. That is to be expected. Okay, you'll only need to adjust the constant b. Right. So, and then the following composition properties are nice. Let x, y, z be metric spaces. Okay, and let f and f prime be two maps from x to y, which are at a finite distance from each other. From each other. So, firstly, if G from Z to X, so Z, G, X, and then Y, we have two maps F prime. That's the situation. If G from Z to X is a map, then I'll say is a map. Then F composed with G and F composed with G prime, they will be at a finite distances, at finite distance from each other. Okay, have finite distance. So under composition, this having finite distance behaves well under pre-composition. So so this is A, and then B. Another composition property is that if you have if G from Y to Z is a quasi isometric embedding. So the situation is X to Y, and then you have finite distance maps, and then Y to Z, you have this G. Excuse me. Then G composed with F and G composed with F prime also have finite distance. In the earlier map, you didn't need a quasi isometric embedding, but here you need a quasi isometric embedding. Okay. So another property is that compositions of quasi isometric embeddings QI embeddings. Okay, and compositions of quasi isometries are quasi isometries. These are isometries, quasi isometries. Okay. So these composition properties well, not exactly turn this into a category, but although I haven't defined category, if you consider metric spaces up to not isometries, but up to quasi isometries or quasi metric, these metric spaces up to quasi isometries, then it won't become a category yet, because you need to make room for this finite distance business. Okay, one of the things that does not happen is that if F and G, X and Y are quasi isometric, you cannot go from X to Y and Y to X and expect to come back to identity like we saw. So up to a finite distance, you come back to identity. So if you take maps which are quasi isometries, okay, and then quotient by finite distance. So you put an equivalence relation that two maps are equivalent if they are at a finite distance from each other. So then that becomes a nice category of sorts. Okay, so you can expect that you can construct quasi isometry group. So let X be a metric space. Okay, and then the quasi isometry group. So of X is defined by Qi of X is basically the automorphisms of X in the, I'll just write a subscript and explain that. So it is in a certain category Q met. So what is this? So you take maps from X to X, which are F is quasi isometry. Okay, and then if F is a quasi isometry, it will have a quasi inverse. Okay, so and then F composed with G, well, G composed with F will be finite distance from identity of X. So what you can do is take the collection of all F such that F from X to X is quasi isometry. Okay, and then quotient these by the equivalence relation tilde. F is equivalent to G if F is equal to G if F and G are at a finite distance from each other. Finite distance from each other. And so these sort of so then the equivalence class of F, okay, in this thing still maps X to X in a meaningful way, right? So right up to finite distance, they they map X to X, okay, and so that is your automorphism in the category of metric spaces.
So in the whole business, you are localizing your category.
Sorry?
You are trying to localize, right? Such that F has an inverse.
Yeah, such that F has an inverse, actually. That's right. So basically, yes. So because there are no inverses, direct inverses, I am trying to quotient so that I can get proper inverses. Now, yes. And so then I get this automorphism. Then I get to say that this automorphism of, or this Qi of X, Qi of X is a group. Otherwise, I don't get to say, because if I don't do this adjustment, I don't get to, like someone said just now, I don't get to say that this is a group. So now Qi of X is a group. So in this category, one can ask for how these quasi-isometric groups look like. Also, one can now consider actions on this spaces, metric spaces, by considering a group embedding into Qi of X, etc. Okay, so action of G. Okay. So the study of this quasi-isometry groups of a given space, metric space, is I guess fairly new or huge topic, so to say. Okay, and yeah, so this is something one.
Sir, where does this G come from? Siphon.
So you take any group G, and then if you can find a homomorphism from here to Qi of X. Now, because Qi of X is a group, if you can find a group homomorphism from G to Qi of X, then you are defining an action, like yesterday's tutorial. Okay.
Okay.
So action is basically that, right? Action on what? Action on X. So G acts on X using quasi isometry. All right. So that's about quasi isometry groups. Now we will talk about quasi isometry types of groups. Okay. So now we'll come back to, so far we were talking about metric spaces and definitions in metric spaces. So now we will talk about groups and put a metric on them using their Cayley graph. Okay, so definition. Firstly, metric on a graph. So let X is equal to VE be a connected graph. Okay, we have Cayley graphs in mind. Okay, then the map V cross V to positive real numbers, okay, equal to 0 as well. Okay? V comma W goes to the minimum of all the paths of length n, such that there is a path of length n. We define paths by using that length for connected graphs. So path of length n connecting V and W in X. So the minimum of that of all such n will be your distance. Okay, so this is rather a metric on associated with X. I guess I will need union 0, right? Because if I take V and V itself, I need just that point. Okay? So that is n union 0. So then that is a metric on this graph. So now we can define. So using that, we can think of Cayley graphs being, having a metric. Okay, any two vertices in the Cayley graph which are connected by a generator in the generating set, they will have distance 1. Okay? So that is the metric on the Cayley graph. So graph actually, but especially on Cayley, particularly on Cayley graph. So now we'll define word metric and word length. Okay, so let G be a group, and so now we are bringing in groups, and let S contained in G be a generating set. The word metric ds on G with respect to S is the metric on G associated to a Cayley graph. And it also tallies with the following Cayley graph with respect to that generating set. Okay, it also tallies with the following. In other words, it's also the following: the distance with respect to S between two elements of the group G and H is the minimum of such that there exist S1, S2, so on until Sn in the set S union S inverse. Okay, such that G inverse H is the product. So you take all such words in S and look at G inverse H expressed in those letters. Okay, so you need S union S inverse, because you should be able to have symmetry from G to H. So here you'll certainly need S union S inverse. Okay, so over there in the Cayley graph, because of the set business, we actually saw that we had a discussion that S inverse is not needed. Okay, many of you find that S inverse is not needed. So even over there, even if we remove S inverse, here we need the S inverse for symmetry. And so this defines a distance for all GH. The distance, excuse me, the distance ds between the identity and G is also called the word length. of G with respect to S. So this is well defined because we are taking the minimum. This is well defined, so you can talk of the word length of G with respect to S. So yes, so a quick example of Z with generator 1. So now we are considering the group Z with the generating set 1. Okay, and then the word metric here tallies with the metric on the space Z. This is a metric space. Okay, induced by R, induced by metric space R. Whereas if you take Z with the other generating set 2, 3 we have been seeing, then this as a group, and this will not tally with the metric induced by. So but that is an uncomfortable situation when we have these groups. So these Cayley graphs are not actually isometric that we saw. Okay, that was our motivation, and hence we wanted to relax that, and we constructed the definition of quasi isometry. Okay, so let us see that indeed if you have two different generating sets, then the Cayley graphs are quasi isometric only when you consider finitely generated groups. Okay, so yeah, I will say that again, that there is a question. I don't see it. Raised hand. Yes, Rana. Yeah, please.
Sorry, the metric.
Sorry, your audio is still not audible.
Now it's clear?
Yeah, it's clear. Yeah, please tell me. I don't hear anything.
Oh, sorry, sir. So please go back to the definition in the metric on graph.
Metric on graph. Okay. Word metric on graph. Yes.
No, not word metric.
Metric on the graph. Oh, sorry. Okay.
Is as a minimality is always exist.
There exists a path, right?
Yes.
It's a connected graph, so minimality will exist. Minimal path will exist. You take all finite length paths of length n, so minimum will exist, right? They are integers.
Okay, so integers, then it possible.
You have to assign the edge length to be 1.
Okay.
Sorry, assign what?
Edge length to be 1.
Integer at least.
Edges are isometric.
They are of length 1.
Yes, then it is fine.
But actually we have done that by defining a path of length n. I mean, the way this is done is we don't define directly a path. We say the path of length n by taking disjoint vertices. So automatically, in the definition of graph itself, we took care of this edge being a length 1.
Yes.
So these are integers, and so minimum well ordering principle. So okay, all right. So I'm sort of short on time. I'll quickly say what I want to say here. Proposition without proof, probably. So let G be a finitely generated group, and let S and S prime be finite generating sets of G. So then the identity on G map IDG, okay, is a bi-Lipschitz equivalence from between the metric spaces. Now we just announce these to be metric spaces by the word metric, GDS and GDS prime. So those two will be bi-Lipschitz equivalent. Okay, so in particular, if X is quasi isometric to, if X is a metric space, XD is a metric space, and X is bi-Lipschitz equivalent to GDS, then automatically it is also bi-Lipschitz, then it is BE to GDS prime. And likewise, a statement about quasi isometries is also true. If X is quasi isometric to GDS, it will also be quasi isometric to GDS prime, because a bi-Lipschitz equivalence is a quasi isometric, not the other way around. Okay. So the proof of this is once again not hard. The main thing to the main ingredient in this proof is finite generation. So what you can do is set a constant C, define this to be the maximum over S union S inverse, the distance between identity and your this particular S coming out of this S inverse. So the maximum, you can talk of maximum because there's a finite set, S union S inverse is a finite set, and so that will allow you, that C will allow you to control distances. Okay, because everything is expressed in terms of the letters in S union S inverse. Okay, so I will not have time to discuss that further. So
it should be DS test. Otherwise, it will be length one always.
Sorry, it should be
S test. Distance means different. S test.
S prime, DS prime in so basically ES will be 1. Right. True. That's right. You're right. So that should be in the other space that I'm talking.
And here S inverse is redundant.
Yeah. Otherwise, it is always 1. So that distance is basically controlled. All right. So without further ado, I'll directly announce that. Yeah. So the idea is to, so this, because GDS and GDS prime are bi-Lipschitz equivalent, they are certainly quasi isometric, and the idea is to study groups, finitely generated groups primarily. Okay, so study finitely generated groups up to, and of course infinite groups, finitely generated infinite groups up to quasi isometric. Which of two groups are equivalent? Okay, so that's sort of a goal of one goal of GG. Okay, and
sir, any two finite group will be there. They will be quasi isometry always.
Yes. So finite groups are not actually very interesting in this sense, because any two finite groups will automatically be quasi isometric. So study finitely generated. That's why I mentioned, I not write it, but infinite groups. You are interested in infinite groups. Actually, if you talk of finitely generated finite groups means what? They are finite groups firstly. So I mentioned this in an earlier lecture that you have finite groups, you have uncountably generated and infinitely generated groups for which there are different techniques. In the middle, you have these infinite groups which are finitely generated. This is the class. This is the actual class or objects of study for GGT RG. Okay, so one of the goal is to classify them up to quasi isometry. Okay, so I will quickly need a definition or a two. I will write those definitions. A geodesic space or a quasi geodesic space. Okay? So first, geodesic space. Okay, so a geodesic of length L. So L belongs to R. We'll define a geodesic of length L. Okay, in a metric space X is a metric space. Okay, with a metric D, we'll also assume that it has some metric. Okay, so in X is an isometric embedding. Okay, isometric embedding gamma from 0L, where the interval 0L, you need a metric on this, right? I'm saying quasi isometric embedding, so you need a metric. This will be from R. Okay, has metric from R. It's an interval which gets it metric from R. So you call the point gamma of 0 as starting point and gamma of L as the end point of. Okay, so gamma 0 starting, gamma L as end. So there is a sense of direction as well on this geodesic. Okay, so the metric space X is geodesic if for all x prime in X, there is a geodesic in X with start point X and end point X prime. So naturally, this is a symmetric relation. So you can exchange X prime and X. So there will be a path the other way, a geodesic the other way as well. So a quick example of something which does not satisfy this is you can take R2 minus the origin. Okay, so you cannot, and that's not a geodesic space. So then there is notion of a quasi geodesic space. So instead of requiring that this is an isometric embedding, if I require that is a quasi isometric embedding of the interval 0L into X, then I can make a quasi isometric, a quasi geodesic space. So I will say, I'll just say quasi geodesic space. Okay, so is a metric space X, and then you do gamma from 0L to X is a quasi isometric embedding. And you say that a space is quasi geodesic space. Okay, if so, what did I say? Firstly, this is a quasi geodesic. This is a quasi geodesic, and you say that a space is quasi geodesic if given any 2 points there is a quasi geodesic connected. All right, so now we are almost ready to state and prove the lemma. Okay, sorry, there's a question. Okay, so we need the following definitions. A proper metric space. You say metric space is proper if closed balls are compact. I'm just loosely stating these definitions. Okay, so but one studies this proper metric spaces and then properly discontinuous action. So a group G is said to act on a space, on a metric space X, naturally by isometries, okay, or quasi isometries, whichever is the case. A group G is said to act on a metric space X properly discontinuously. If for every compact set K contained in X, okay, for every compact set K contained in X, the set of all G such that the K and GK are not disjoint. Okay, this set is finite. If this set is finite, then you say that this action is properly discontinuous. Okay, so examples of properly discontinuous action. The action of the fundamental group by deck transformations on a universal cover. Okay, so if you have a base space and a covering space, universal cover for that matter, and then the action by deck transformations is an example of properly discontinuous action. So in fact, that is a guiding example to stating the fundamental theorem. So the example that I will give you is that of tessellation by octagon. You might have seen this. Okay, then there are further octagons. So there is a regular tiling, tiling of the whole hyperbolic plane. So I'm using the Poincare disk model. You can draw an equivalent picture in the upper half plane model. So you will have octagons. Okay, so like that, this is an octagon, and then it will be regular. Okay, because the lengths, the geodesic sides have equal lengths. So this is a Poincare disk model. It's easier to picture there. Okay, and then you see that you can actually, for each of these fundamental domain of action by the pi1 of the surface of the genus 2 surface, put in PSL2R appropriately, so that you get a octagon like this. Okay, so if you take the representation of pi1 in PSL2R, you get this action on the upper half on the disk model, let's say. Then it is not PSL2R. If I need PSL2R, then I need to stick to upper half space. So if you take the isometry group of this one, then and put pi1 in the isometry group of the Poincare disk model, isometries of this one, then you see that you have this fundamental domain being displaced further and further into smaller and smaller octagons like that. I mean, smaller visually, they are all same area actually. Okay, and then you can consider for each fundamental domain of action like this, you can actually, put a vertex and imagine a dual graph, so to say. Okay, So, and now if you consider the dual graph, the vertices are moved to adjacent vertices by so-called the generators of pi1, okay, which are isometries now, okay, and so pi1 is finitely presented. Pi1 is we already know that surface groups are finitely presented. We saw the presentations, but the fact that this phenomenon generalizes to groups and allows us to conclude that groups are finitely generated is actually the fundamental theorem. Okay, so here's a statement. The metric version of this theorem says the following. So here is the so let X be a proper geodesic metric space. Okay, and suppose that a group G acts properly discontinuously on X via isometrics. Okay. If the quotient by the group action is compact, okay, then the conclusion is on the structure of G, then G is finitely generated. Okay. An awesome achievement there, that you can conclude G is finitely generated. And furthermore, and G is quasi isometric to the metric space X. So more precisely, there is a word metric. There is a word metric for G, so that for any point x0 in X, the map from G to X given by x0, G goes to Gx0. This defines the Gx0. So G is acting on X, right? So Gx0 is a quasi isometry. So the quasi isometry is given by that kind of map. So the motivating picture for this theorem is precisely this. Okay, so you have X by G is compact. So if you have the group action, when you take the metric space and then quotient it by group action, you have a compact metric space, then you can basically say that the group is conclude that the group is finitely generated. In fact, the generating set is going to be precisely the ones which move a vertex to nearby vertex in this kind of dual graph. Okay, so actually you can have a finite set of stabilizers of that vertex as well. So that's allowed. Okay, so because this action is not a free action, you can actually allow a finite stabilizer set for that set. Okay, so although in the case of pi1 of surfaces, this action is a free action, so it's not only properly discontinuous, it's also a free action, but we don't require that in this theorem. So that's the fundamental theorem. I am really excited to present the proof using this picture. However, for shortage of time, I'll do it during the tutorial. Okay, so I'll quickly go over the proof of this as well. Okay, so it was this brings me to the end of these lectures, and it was great fun teaching here. Thank you, Professor Abhijit Pal and Professor Tiken Singh, for the opportunity.
Yeah, thanks very much. So maybe
Thank you.
there is a option of giving clap.
So you have clapped using the icon. Okay.
Yeah, so thank you very much. So any questions?
Yes.
There are some.
Can we get a metric on x by g naturally? Yes, Rajesh Day. Yes, true. We can get a metric on x by g. In fact, the proof involves giving a metric, and then using that metric, we'll say that x by g has a diameter, and that diameter ball is what will allow us to prove the result. There's a dual graph of tiling of hyperbolic space by octagons is Cayley graph of pi1 of S2. There are relators coming in, and I think there are relators. I think so. Yes, I think that should do. But I should verify that carefully. But I think that should do. I'm not certain, but I think that is right. Yeah, it's nice. Very pictorially it connects very nice. How the relators look. So you see that these octagons, these octagons, you can actually go from here to here. So there is a cycle like that.
So even if you take this tessellation, 88 tessellation of the poikilometers by this octagon, so that will give you a graph, right? That in fact it is the Cayley graph of this fundamental graph.
Of the fundamental group. If I take the tessellation by this one, yeah. So this one you are mentioning, right?
Yes, yes. Right.
Yeah. Okay. Yes. Yes. So that I think is the question. Looks right. Yeah. That's the Cayley graph, right? Yes.
So there is another. Say, Orkojit, you want to ask some question?
Yeah, sir. Can you discuss? Give some examples of that quasi isometry group.
That is tough. Actually, see, the reference I'm looking at is Clara Lowe. And here, very few examples are mentioned. In fact, there is a paper by Parameswaran Shankaran, which talks about the quasi-isometric group of Z. That itself is very huge. So Professor Paul can probably add something to this. He probably knows more.
Yeah.
Yeah, quasi-isometric groups of groups.
Okay, thank you.
So yeah, I also don't know explicit result.
Who has paper for quasi isometry of Z?
Sorry?
Who has some paper for quasi isometry of Z?
Parameswaran Shankaran. Yeah.
Sorry?
Parameswaran Shankaran.
He has some result on this quasi-isometric.
Quasi-isometric group of Z. Just Z, you see. So, yeah.
And what branch of mathematics do people study for infinitely generated or uncountably generated infinite group?
Uncountably generated. See, I don't have a exact this thing, but Lie groups are uncountably generated. That I know. So it's the other way I'm saying that if you look at Lie groups, every neighborhood of identity has generators. So that is uncountably generated. But if you tell me that the group is uncountably generated, of course, I can't say it's a Lie group. So I don't know the answer. So which branch of mathematics studies that? I don't know. Yes.
So there is something called this Mosto rigidity problem, right?
Yes.
Hyperbolic 3 manifold, closed hyperbolic 3 manifold.
True.
So if I take two of those things and the fundamental groups are
Isometric, isomorphic.
Isomorphic.
Right? So this means that they will be quasi-isometric to each other. Quasi-isometric. So does it give you a homomorphism from this, from one free manifold to another?
I think so. At least in the closed case, they will actually be
problem.
Most of rigidity.
Most of rigidity. If two of them are isometric, then the underlying topological manifold have to be homeomorphic. Has to be homeomorphic. Or Yeah, if pi1 is actually in a closed case, sorry, your question is if the pi1s are isomorphic, the manifolds are actually same.
I think most of it is about isometry, right, or what?
Yeah, isometric. Correct.
Yes. I mean, there is a isometry that induces this isomorphism.
Correct. Correct. But I don't know much about this quasi-isometric group.
Yeah, I think the examples are sparse. Actually, if I look at this paper also, it's not very old or anything. So only, I mean, that's why I said only Z. I mean, my surprise comes from the fact that, yeah, there are no.
I think if I take the X to be a compact metric space, then every map will be close to, I mean, will be close to identity, right? So then it won't be very interesting.
If you take X to be compact metric.
Compact metric space, yeah. If I take it as a compact metric space, then every map will be close to identity, right? I mean, yeah.
Every quasi-isometry.
Compact space
for what? I don't understand. I mean, you take compact metric space for what?
I'm taking, suppose I want to calculate the quasi-isometry group for a compact metric space, right?
So compact
the question is about groups.
For compact, it won't be very interesting. That's what.
That will be identity group, right? Because it,
yeah, it will be just a singleton.
And in the
same, is quasi-isometric to a point, right? So that group is not interesting.
Yes. However, I mean, the question is about quasi-isometric groups of groups.
Okay.
So, yeah, I mean, you are talking about a metric space. But I was talking about, you know, in general, groups.
Okay.
Well, metric spaces as well, compact, yeah, it's pretty.
I want you to, I mean, say something on that point where you said that if is a, suppose X is a metric space and I am considering some quasi-isometry F. So then that F need not be at finite distance from identity, right? Suppose suppose you have a metric space X and you consider a quasi-isometry.
Quasi-isometry from
yes,
X to
X to X. Yes, yes.
X to X, okay.
So now that F need not be at finite distance from identity, right?
It need not be finite distance from identity. There will be a quasi inverse to it.
Yes.
Okay, and so F composed with that quasi inverse will be at a finite distance from identity. And yeah, F itself it need not be at a finite distance from that. Scaled and finite, that's all I can conclude. So what example do you have in mind when you say that?
I don't have, I mean, I think in literature there could be some examples, but I want to know the example.
See, I mean, if it is a, if F is a quasi isometry, then there is an inverse. So the composition I can say is at finite distance, but this itself, it's a quasi isometric embedding.
Yes.
With a quasi-dense image, right? So it should have quasi-dense image. So basically that is less than or equal to C. So yes, it will be, you know, at a finite distance from identity.
It should be.
So right, I mean, that characterization probably will give you that it is at a finite distance from identity.
How is that? Let's say you want to prove that fx, x is bounded by something, right? You mentioned this point.
Yes, yes, that's the
This one,
characterization.
okay, where is it?
Let me go back to that theorem.
Hi, here, first one.
Yes, alternative characterization. This one, quasi dense image. So there will be a quasi dense image for each x. There will be f of x, which will be bounded distance like that by universal.
What you want? You want distance between fx comma x is bounded, right?
X is bounded. Yes, that's the one.
So how do you do that?
This one, this quasi dense image. You consider the image of f. Okay.
Yes.
So x and fx
Yes.
will be at most at a distance c.
That is the point. Why? Can you just write? I'm unable to.
Yeah, see.
I mean, this says that for any x there is some y. For
Yeah.
each
So,
fy comma.
no, for any x there is an x. So for x belongs to x, there is a some other p, such that f of p and x will be at most at a distance c. Right? So this is identity of x.
No. You want, I mean, distance between f and identity that is bounded. That means you want f of x comma identity of x that is bounded, right? For all x.
Yes.
So here you have to show fx comma x is bounded by some constant.
That's what I'm doing.
That is fp and x, right?
Oh.
I mean, the counter example should come from groups, I think.
Okay.
Or Abhijit sir can say something from.
Okay, we can discuss again in detail.
Yeah.
That is
Yeah. So lecture, I guess we can stop here.
Please stop the recording.